BNSF Railway. And just a little bit of background on what our team does. Some of our basic kind of core responsibilities really deal with probably the most important thing that we do, which is prevention of hazardous material incidents across our network. We look at all different aspects of the movement of hazardous materials by rail. And, from a prevention standpoint, we're looking at different technologies and policies and practices as a railway in which we can put in place to help minimize the risk of hazardous material incidents. We also deal a lot with preparedness, so we spend a lot of our time out there in working with communities, first responders. Training like this is historically been very, very important for us, and again, we spend a bunch of time with this. We also develop plans and pre-stage equipment across our network to make sure that we're able to respond effectively if we do have an incident. Finally, kind of the third leg of that stool is response. And so, while we never want an incident to happen, the likelihood of it happening is low, but we also understand that there's a chance of it. So, a very important part of what we do is being able to effectively respond to hazardous material incidents. A little bit about the webinar. So, for a long time we've been doing community hazmat training. Clearly, this is a different year in a lot of ways. For us, it's really impacted our ability to get out and somewhat be face to face with different agencies across our network. So, a few months ago, we started the webinar series, and up to this point, we've been doing our basic class, which is the Community Hazmat Awareness and Response class, and I hope that you guys are familiar or have attended that. If you haven't, I strongly encourage you to do that. That is kind of that's the basis for all first responders and information that we want them to understand when responding to a rail incident. So those classes plus 3 additional webinars, including this one, are all available on our website at www.bnsfhazmat.com. You've been there, you signed up for this one, so you know where that stuff's at. This class, Railcar Knowledge for the First Responder, really came about because of the Community Hazmat Awareness and Response webinars that we've been doing. So this is the first of this class that we're doing. There's going to be 2 others as well to look out for: the Locomotive Awareness and Response class and Initial Response to Rail Incident. So, why those 3? We took feedback from the webinar and created these classes based upon what you guys were telling us that you wanted to see, and for us to provide some additional information. So at the end of the webinar, you guys are going to get an email, and there's going to be an opportunity to fill out a survey on there, and we really take that to heart. We want your guys' honest feedback about this webinar and any comments. We're going to continue to do these, so our goal is always to try and make these better if we can, and so we want your guys' feedback as to what you think about the webinar. From a housekeeping standpoint, there's Emily Spears is helping out as a host on this, and James Farner is manager of hazardous materials out of San Bernardino, California. He's also on the webinar. And so how we're going to do this, I'll run through the webinar. James is on, and he's kind of monitoring the chat feature. So what we'd like you guys to do, if you have any questions, is to use that chat feature. And when you do it, make sure that you're responding to all participants on there. That way everybody gets to see the question, because if you've got it, you guarantee somebody else is probably thinking the same thing as well. So we'll respond to those. James will respond to those questions, really, so there's no, you don't have to wait for something. If you guys come up with a question, go ahead and throw it in there, and James is going to work on getting that answered for you guys. So with that, we'll go ahead and get started. So kind of what we're going to go through this evening is the BNSF Hazmat team. introduction and history of rail equipment, types of rail cars, and response considerations. Then we'll kind of wrap it up with that. So we'll dive into, really what a first responder should understand about rail cars when responding to a rail incident. The content is not designed, as a comprehensive study. This is awareness. That's what our intention is. And, really for the safe response to leaking or derailed rail equipment. The information should provide awareness to you as a responder so that you can maintain mindfulness and awareness when on scene and to help better understand risks associated with potentially involved rail cars. There's a reference material which is displayed there, which is a field guide to tank cars, and the American Association of Railroads put that out. It's available through our website, or you guys can Google that online and find more copies as well. A lot of the information that we're going to be going through this evening, you're going to be able to find again in that document. And so it's a great resource. Download that. You guys can save it, print it out, whatever's best for you with that. But that's going to be a good reference for you guys. This is the BNSF Hazmat team. You can find contact information here for whom you should reach out to for additional questions on any of the material we're covering tonight or other rail matters. Additionally, on-site instruction or training specific to your department's level of training is available by reaching out to the Hazmat Manager or Director as shown on this map. This training is provided free of charge, and the slide, I'll show it again at the end of the presentation for additional reference, but again, you can find this available on that bnsfhazmat.com website. So let's get started. We'll begin with tank cars and the construction of rail cars. Tank cars are the rail car that most bulk hazardous materials move in. In this course, we'll discuss these cars and what you need to understand about them when they're involved in an accident or are leaking. Accidents are rare, but they do happen. We all need to ensure that we're prepared. Leaks from these cars can occur as a result of an accident, such as damaged valves or a punctured shell. It can also occur as a result of a non-accident release, with valves, fittings, appliances not being properly sealed, or possibly failing even while the car is in transportation. From looking at this picture, what can the responder learn? There are certain things that we can understand about this car simply by looking at it. Does it contain a liquid or gas? Can I expect the car to be under pressure? Is it a jacketed or non-jacketed car? Is there hazardous material in the car? If so, what is it? These and more questions can be answered quickly and effectively from a safe distance by a responder. How did we get where we are today with the transportation of bulk hazardous materials by rail? Let's look at where this all started. In order to help him maintain control of the booming oil industry in the 1860s, J.D. Rockefeller turned to the rail system to create a competitive advantage for Standard Oil to move his crude oil to refineries. At first, oil was moved in wooden barrels strapped to flatbeds, or the Densmore car that you can see in that picture. This led to many leaks, as you can imagine, accidents, and were often stolen. The first cylindrical car with a dome was designed and produced in 1869 to move crude oil. This was the first car that began to resemble the current tank car design. Since the 1860s, railroads have pioneered the safe transportation of hazardous materials. Today, tank cars are some of the most robust and strong packages for transporting hazardous materials that exist. While the package has gotten stronger, we always see a risk of release from these packages while in transportation or at terminals. This is due, again, to the potential for the non-accident release or potential for an accident while the car is in motion. This picture shows a new DOT 117 tank car that is used to transport various hazardous materials that can be liquids or solids at ambient temperatures and pressures. It's important for a responder to understand how tank cars are constructed. When responding to an incident, this knowledge can help you better understand the nature of the problem and to understand what is needed to mitigate the issue. Let's start with how a car is made. Cars are made at various locations in the U.S. and Mexico. Key Fine 128B steel plates are rolled into rings, then fusion welded together. The heads are a single piece of steel that are pressed into shape and fusion welded to the rings. Once the cylinder is welded, appliances, stud seals, and other parts are welded onto the tank. The entire tank car is subject to a very controlled heat treatment process called normalization, where the entire car is brought to a certain temperature and slowly cooled to ensure stronger welds. The steel used today for cars is very strong and ductile. We want it to bend and flex in accidents rather than crack and break. Some tanks are made from aluminum or nickel due to compatibility requirements for their service. A good example is most of your hydrogen peroxide cars will be in aluminum cars, as hydrogen peroxide will react with steel. Nickel or stainless steel alloys are commonly used for cryogenic tank cars to help with better transition temperatures due to the extremely cold nature of the products. This slide shows various thicknesses of tank car shells that we'll find in rail transportation. The thickness of car is clearly related to the overall strength of that car. Thicker cars are typically used to transport gases which are under pressure. The thicker shell provides additional protection to the car and commodity from damage or punctures. Towards the right, you will see ISO tanks or intermodal tanks in the representative thicknesses. These tanks are much thinner and resemble transport trucks that move hazardous materials by road. Finally, the 1/8-inch stick represents either an IM102 ISO tank and is also the thickness of the tank car jacketing that we'll discuss later. As a first responder, remember that there are really 3 types of tank cars. Knowing and understanding these different tank cars can help you to understand some of the properties associated with the material that they are hauling. Questions we should ask ourselves when dealing with a tank car. Is it a liquid, gas, or solid? Is it something that could be under pressure and wants to be a gas if it is released? How does that affect our decision making when we understand the types of cars that are involved? Let's discuss the differences, and you'll get an opportunity to see as we go through the course. So going through the 3 different types of cars, we have a low-pressure tank car. That represents over 70% of the fleet that's currently out there by rail. Big characteristics for that we look for, those tank test pressures are going to be up to 100 psi, which is about a fifth of the tank burst pressure. 165-pound working pressure for the car. They haul both hazardous and non-hazardous commodities. Second type of tank car is a pressure car. Fewer of these, about 25% of pressure cars make up the fleet out there. You'll hear occasionally high pressure tank cars. A lot of times when a firefighter thinks high pressure, he's thinking of his SCBA, which is up to 4,500 psi. These tank test pressures for pressure tank cars are typically tested between 100 and 600 psi. So we're not talking about extremely high pressures, but they are higher. These move hazardous commodities, and generally what you're going to find in there is some type of a liquefied compressed gas, but not always. There's some liquids that shippers will choose to transport in those stronger cars. Cryogenic cars, these are typically low pressure. However, CO2, which is a liquid cryogenic materials, is shipped in a DOT 105, which is a pressure car, because of the pressures associated with that. Most move inert atmospheric gases like that CO2 and argon. There are some, however, of flammable liquid ethylene, which is a flammable gas, or anhydrous hydrogen chloride, which could be a toxic or corrosive gas. Nitrous oxide, it moves occasionally by rail, but there just aren't that many shipments of that material out there. So what is the tank car specification? Specification is a set of standards or regulations that specify how a car is to be designed and constructed. This includes the type of materials for the tank, the plate thickness or the shell thickness, type of welding or plate connections, and the vessel pressure ratings for it. Tank cars are built to a specific standard as indicated by the car type. The authorizing agencies include the U.S. Department of Transportation, Transport Canada, and the American Association of Railroads. Specification must be stenciled on 2 sides of all railroad tank cars, and it's going to be found on the right-hand side of the car. What's the specification look like? First, what you're going to want to do is find the tank car specification on the right-hand side of the car. See the circled item above where the car stencil is located. That's the specification. The first part of the specification is the authorizing agency. Second part is the car class number. The third is a delimiter letter. A means nothing unless it's a DOT 113, the cryogenic car, in which case it represents the minimum loading temperature that's authorized for that specific car. J would indicate the car is jacketed and has head shields. P indicates the car is built to a performance standard. R tells us that it is a retrofit car, and S indicates the car has head shields. T tells us that it has sprayed-on thermal protection. The fourth part of the car specification represents tank test pressure. Again, tank test pressures of 100 or less indicate that the car is a low-pressure general service car. Tank test pressures above 100 indicate that the car is a pressure car. Materials of construction would be next if the car is made of something other than steel, such as aluminum. W indicates that the car is fusion welded. Certain next-generation pressure cars for TIH, toxic inhalation hazard, poison inhalation hazard materials, may be represented by an I here. Finally, the last number indicates certain fittings or characteristics the car has, including rubber liners if present. The rubber liner would be indicated by the number 5. For more details on the tank car specification, there's too many really to cover here. Again, reference that AAR field guide for tank cars. It's got a complete listing in there for you guys. Other markings that can be found on tank cars that can help a first responder, these include the reporting marks. This is clearly the unique identifier for the tank car, what we refer to as a license plate for that tank car, and that's how we're going to communicate the car and identify it on a train list or consist or billing. There's tank capacity, qualification stencil, build date, and the weights of the car. The reporting marks are what we'll use to positively identify the car. They will always be found on the left-hand side of the car, regardless which side you're on, and on the ends of the car. Sometimes reporting marks can also be found on top. Think of those, again, like a license plate for a vehicle. In North America, you're never going to find two that are the same. To quickly estimate the capacity on a loaded car, look at the end of the car. The capacity listed is for a volume of water that fills the car to 100% capacity. Cars in transportation are not filled to 100% capacity to allow for contraction and expansion of the product as the temperature changes. Generally, cars are filled from 95 to 98% of capacity. If a car is accidentally filled to 100% of capacity, or if the temperature is extended, the product to fill all of the vapor space, the car is considered shelf full. This will likely cause a release of product through the pressure relief device. The largest capacity for a car by regulation is 34,500 gallons. Cars will be sized based upon commodities they intend to move. Heavy dense materials such as something like sulfuric acid would move in a much smaller car, maybe only 13 to 14,000 gallons. On the other hand, liquefied petroleum gas or propane, being much less dense, could move in a much larger car up to the 34,500 gallon capacity. To determine the weight of a completely empty car and load limit weight, look at the left-hand side of the car, and this is going to be found underneath your reporting marks. Empty weights vary by the type and size of the car. Hazmat tank cars are either regulated to a 263,000 pound capacity or a 284,000 pound capacity, with a car using different axles. This would include the weight of the entire car plus the commodity. Remember, even empty residue cars are going to have some amount of product remaining as a heel, so the true empty weight of a residue car may vary from what's actually stenciled on the car itself. The tank car qualification stencil is on the right-hand side of the car, generally next to the placard. We'll call this the hazmat corner. It is information that is helpful to the first responder and to hazmat responders that may work on this car. What we find here are many different things. Helpful to us is obviously the placard and product shipping name. It's required. The car specification, information on the opening pressures for the PRD or braking disc if it's equipped, the last inspection performed dates and the due dates, along with car manufacturer or the build date. For response, we always start in this corner. It gives us the critical information to understand which car and commodity we're dealing with. A rail car really has no front or back per se. It'll happily go in either direction at full track speed. To communicate orientation of damage to a car or where leaks are observed, we orient the car in a specific way. This helps us to communicate with each other about what we see in the field. To begin, look for the handbrake on the car. This handbrake is used in a similar fashion to an emergency brake on a vehicle. The responder can turn the handbrake clockwise to apply the manual brakes to an individual car. The end of the car with handbrakes is what we call the B end of the car. If that's the B end, the other end of the car will always be the A end. We always orient ourselves to the car from the B end. If looking at the B end of the car, the right side of the car will be on our right. The left side of the car will be on our left. Axles will be counted from that B end. As an example, the first axle we see from that handbrake will be number 1, all the way to the right, the A end of the car, which would be the 4th axle. We will also use upper and lower terminology to determine if damage is found in the upper half of the tank or the lower half of the tank. As an example, we may describe damage or an area of concern to be in the A end upper right section. All tank cars in use today will have vertical restraint system that is referred to as a double shelf coupler. These couplers help to prevent uncoupling and derailments or during switching operations. The uncoupling or bypassing of a coupler can lead to a puncture in the head of an adjacent tank, to create a catastrophic release of product. Other cars in rail transportation more commonly use the traditional coupler you see on the left with no restraint on the top or the bottom. These car couplers separate easily in an accident. Rail cars are held onto their truck assemblies by only gravity using the shear weight of the car. The connection point between the tank and trucks is what is referred to as a center bowl. A pin is used for aligning the car and truck when building the set. During an accident, it's expected that the trucks and the car are going to separate if it's overturned. The truck assembly can weigh nearly 10,000 pounds. Careful if you ever see an overturned car that still has a truck assembly attached. It could just be precariously bound to the seal, but able to fall with any sort of movement of that car or truck assembly. Here's a closer look at the truck assembly. Our primary components here are the primary bolster, which is the center bowl, which is on top of the bolster. The springs, which act as suspension for the car. Wheels with sealed roller bearings. The side frame, which connects the wheels to the bolster. And side bearings, which act as the side-to-side roll limiters. In an accident, you can expect again that all of these are going to be easily separated from each other. We'll start to look at other features that a tank car may have. Some cars may have a tank car jacket, which protects either insulation or thermal protection or both. The purpose of thermal protection and insulation are very different from one another. Insulation is used to regulate the commodity temperature change for what occurs normally in transportation. Think of that keeping asphalt hot or carbon dioxide cold for as long as possible with the help of insulation. This insulation is typically made just from fiberglass or urethane foam and does not provide significant protection to the car if it's involved in a fire situation from either a pool fire or direct flame impingement. The car has thermal protection, is commonly wrapped in a half-inch thick ceramic fiber blanket. The blanket provides protection to the car to help it survive in a pool fire to direct flame impingement. The intent is to slow the transfer of heat to the commodity and to protect the steel, which does not have liquid behind it, acting as a heat sink. A car with thermal protection and without other damage is expected to survive in a pool fire for at least 100 minutes or to direct flame impingement for 30 minutes with no outside intervention such as cooling. During this time, it's likely that the PRD will activate to release pressure or product. Thermally protected cars may also be wrapped with fiberglass insulation as a means to help control the product temperature. As discussed On the last slide, a jacket, 1/8-inch thick or 11-gauge steel, is used to protect the thermal protection or insulation from damage and weather. It's important for a first responder to understand that if a car is jacketed when looking at damage such as dents, punctures, or tears, jackets are not part of the structural integrity of the tank. Damage here does not affect the ability of the tank to contain the product. It is also important for a responder to understand if a car has a jacket when the car is involved in a fire to determine appropriate effective control techniques. We're not going to talk a lot about tank car fires, but just understand that the presence of a jacket may hinder the ability to effectively cool a car with water. Tactics will need to be adjusted for cooling jacketed cars. The easiest place to determine whether a car is jacketed or not is to look at the body bolsters. These bolsters are welded to the tank on each end and connect the car to the center bowl of the truck assembly. If you see that the top of the body bolster, as shown in the top left pictures, completely covers the bolster and has a hood look to it to shed water, that this is a jacketed car. Other clues for a jacketed car could include the presence of small inspection packages on the tank sides or ends, thin lap welds on the sides, or horizontal welds across the heads. Remember that the heads of these cars are single pieces of pressed steel. As always, you can work with a railroad hazmat team member to confirm whether or not a car has a jacket. Many tank cars will have a head shield to help protect the end of the car. These shields are an extra 1/2-inch thick plate of steel to help deflect energy and prevent puncturing of the car in an accident. In some cases, you may physically see the head shield on a non-jacketed car, but in most cases you're not going to see the head shield as it's integrated into the jacketing of the car. We'll now discuss differences between the 3 different types of cars that we mentioned earlier that move hazardous materials by rail. The first we'll look at is a pressure tank car. This car moves only hazardous materials and is designed for materials that would generally be gases outside of containers at normal temperatures and atmospheric pressure. Examples of commodities that are commonly transported in pressure cars are liquefied petroleum gases such as propane and butane, and hydrous ammonia, chlorine, along with possibly other liquefied compressed gases. Common car classes that you'll find for pressure cars are the DOT 112s and DOT 105s. In some cases, shippers may use the stronger pressure cars that offer more protection for various liquids. An example of this would be where some shippers use a pressure tank car to move natural gas condensates. This is a Class 3 flammable liquid. Pressure car test pressures are again from 100 to 600 psi, and the capacities range up to 34,500 gallons. Things we can assume about pressure cars: they're likely under pressure, although not always. You got to remember what is based upon the ambient temperature outside and possibly the boiling point of a material. Could be close enough to each other where there's very little pressure inside the tank car. Some commodities like ethylene oxide or these natural gas condensates don't generate a lot of pressure. Tank shell steel thickness is typically from 9/16 of an inch to 1 1/16 of an inch. Most pressure cars have jackets, thermal protection and insulation, and all are going to have double shelf couplers. All valves and fittings are protected in a protective housing on top of the car. It's important to remember that as the outside temperature increases, internal pressures also increase. As a general rule of thumb, if you only see one housing and nothing else on top of the car, it's going to be a pressure tank car. Looking at the pictures here, these are protective housings that we'll find on top of a pressure tank car, such as a DOT 112. In this protective housing are all of the valves and fittings that are necessary for loading and unloading the tank, along with the safety relief valve. Terminology here: we have liquid valves with siphon pipes or reduction tubes underneath them. These run lengthwise with the tank, the 2 valves that you see in the pictures running lengthwise. Those siphon pipes, reduction tubes, will go near to the bottom of the tank, and we're either going to load or unload the cars through those pipes. A vapor valve off to the side just extends into the vapor space of the car. There could be a thermo well on the car. That's a sealed tube we'll talk about later. Gauging device. The most common type of gauging device we're going to find is a magnetic gauging device that you see in both of those pictures. Here we are looking at common valve arrangements for a DOT 105 tank car used to transport chlorine or sulfur dioxide. Could be other materials as well. Same thing here. We have liquid valves running lengthwise with the tank with induction tubes, vapor valves off to the side, and a safety relief valve in the center of these. The industry has eliminated additional openings for thermal wells, sample lines, gauging devices from these cars, really in an effort to help reduce the potential for leaks from those components. Underneath, most valves and fittings in pressure cars are excess flow valves or check valves. These are designed to operate in an emergency, either at loading or unloading facilities if there is a sudden release that's detected, or in an accident if a valve is sheared off the car. As pressure and or liquid try to escape from the car due to a sudden change in pressure, the check valve will seal and stop the majority of the flow. These are metal-to-metal seats and won't totally stop the flow, and there may be some seepage, but it'll stop the majority of product release. Fittings that will not have check valves on pressure cars are the safety relief valve. We always want that thing to work. Gauging devices, thermal wells, and vapor valves on the chlorine cars. In this photo, you can see where excess flow valves prevented a catastrophic release through a sheared off vapor valve on an overturned and loaded propane tank car. The magnetic gauging device allows us to determine product volume in a loaded car without the release of product. This sealed system utilizes a floating ball which will float on top of the product in the car. The ball moves up and down on the rod depending upon the height of product in the car. On top of the car, we remove a rod cover to expose the measurement rod. We pull this up until it engages the ball via a magnet. The measurement of that rod at that point tells us how much vapor space or outage exists in that car. The ball and rod only travel about a third of the way down into the car, so it's not going to work for partial or residue loads. As with everything in this housing, only trained responders should access and use that gauging device. There could be a damage to the internal tube from an accident that may contribute to a release if the rod cover is inadvertently removed. Many pressure cars will have a sample line available in the protective housing. Chlorine will not. This needle valve extends into the liquid of the tank and can be used by customers to obtain a small sample of product of the car prior to unloading. Responders are going to use the sample line as a means to measure pressure in the car. The 1/4-inch NPT thread allows for easy hookup to insert a pressure gauge as seen in the photo. We can use this to help us understand what may be happening with the car or to assess a leaking condition. A thermal well may also be found on pressure cars, except chlorine cars again. This device would allow a customer or a responder to accurately determine the temperature of the product in the tank. By removing the threaded cap, we can insert a thermometer on a chain. Inside the tube is ethylene glycol, which will transfer the temperature reading to the thermometer. An overturned pressure car may leak slightly through this cap if it is not fully tightened down. You'd be able to determine this if it's ethylene glycol because of the color associated with it. Also, most products in these cars are going to rapidly convert to a gas once released, so the presence of that liquid would generally indicate that it's something other than the commodity that's coming from the car. A pressure relief device will be found on all pressure cars. This device is a safety feature intended to relieve abnormal pressure increases within the tank car. On pressure cars, the PRD should never operate under normal conditions. However, in the event that the car is exposed to fire, an internal chemical reaction creating pressure, the tank car is overfilled, or there's a mechanical defect with the spring, then we would expect the valve to release product or vapor. Note that liquid CO2 is shipped as a cryogenic liquid in a pressure car and will release through regulating valves, which is different than this PRD. We're going to talk about that in a little bit. Set pressure for the PRD can be found in the car stenciling on the right-hand side of the car. The set pressure on a tank car may not be lower than 75 psi or higher than 1/3 of the tank burst pressure. As an example, a DOT 112 J340 tank car with a burst pressure of 750 psi will have a PRD that's set to 247.5, or 1/3 of the burst pressure for that tank. PRDs may be either internal or external, which references where the spring components are located. Internal PRDs have their spring and components exposed to the product inside the car. In this case, we're not concerned about corrosion properties of the product on the spring. Some cars, however, have external PRDs where the spring is outside of the car and not exposed to potentially corrosive material, which would degrade the springs over time. As an example, chlorine cars are going to have an external combination valve, which is further protected by a rupture disc, which seals commodity from the car to the pressure relief device. LPG is going to have an internal valve. All right, let's talk about the other type of tank car that we have. Again, most common that you're going to find out there, which is the low-pressure general service car. While this car commonly transports hazardous material, it's also commonly used to transport non-hazardous liquid commodities. We can find soybean oil, corn syrup, lube oil, lime slurry, and even beer. Hazmat commodities include crude oil, ethanol, acids, bases, oxidizers, along with many others. The physical properties of materials transported in these cars will be liquids or solids under normal pressure and temperatures. DOT and Transport Canada regulations reference this car as non-pressure. However, the term is misleading. It's likely that there is always some amount of pressure within the car, and that's important for a responder to understand. Generally, that's why we'll always refer to these as low-pressure cars. There are differences we will discuss with the low-pressure car and how they are constructed. As you can see in this photo, an easy way to visibly distinguish a low-pressure car from others is to look for multiple appliances or features on top of the car. On this car, you'll see the PRD on the left, valve housing cover with valves underneath it in the center, and a manway on the right. Remember, a pressure car typically only has one protective housing on top. New general service cars have fewer exposed appliances on top, but will generally still have a valve protective housing and a manway. General service cars may also have a bottom outlet valve. The car test pressures are 100 psi or below. General service cars, shell thickness is typically anywhere from 7/16 of an inch to about 9/16 of an inch. Some cars are going to have a jacket and thermal protection as well. Here's a list of common fittings that you're going to find on a general service low-pressure car. These are typically designated by the car owner in the shipper for their specific needs for their receiving, loading facilities, or the product itself. And cars may or may not have them. There's a lot of different manufacturers out there for valves, so not all ball valves are going to look the same, and pressure relief devices are going to be made by different manufacturers and maybe different sizes and ratings and shapes as well. The required fitting that's always going to be found on this, regardless of other appliances, is always going to be the pressure relief device. That's a requirement for the cars. Here are some of the common appliances that we're going to find. There's a manway, the upper left, that can be used to load or unload the car, used to access the car if needed for cleaning and inspection, and can also be used to vent the car during unloading. We find that most issues we have with low-pressure cars have to do with this manway. It may have either not been properly secured by the shipper with loose bolts, they could have no or bad or deteriorated gaskets, or the lid itself could be warped from over-tightening and not provide an efficient seal. In the lower left photo, you see a fairly common multi-valve housing area. This has our liquid and vapor lines. On this car, it also has a sample line, thermal well, and a gauging device. All of these components are attached to fittings or pressure plate. In the upper center, you'll see a common vacuum relief valve. This is designed to eliminate vacuum buildup in the car from product temperature variation or from unloading and not properly venting the car. Finally, on the right, you'll see two types of pressure relief devices. Again, internal and external. These are similar in function to what we've discussed on pressure cars. On the lower right, you'll see a rupture disc assembly. Some cars that transport non-flammable, non-toxic liquids have a rupture disc assembly, or referred to as a vent, which is on top of the car. This rupture disc will alleviate pressure, but does not reclose as the valves will. We can quickly determine if a car has a rupture disc or a valve when looking at the stenciling, again, on the right-hand side of the car. If it says valve, it's a reclosing device. If it says vent, then it is a non-reclosing rupture disc. Some additional items we can find on low-pressure cars. Top left, you'll see a different type of gauging device. This would be welded to the inside of the manway nozzle. The number of inches indicated would represent the number of inches of outage or vapor space. A tank car outage table could then translate that number of inches to gallons. On the lower left, we have a common bottom outlet valve assembly. This is a quarter-turn ball valve, and in this case, it's a newly designed disengaged valve handle. You can see the bottom outlet valve nozzle with silver cap in the photo. This would be removed to unload the car through the valve. Bottom outlet valve caps have a rubber gasket and are considered a secondary closure, meaning that even a failed valve would not leak through a properly secured cap. Additionally, in this picture, you can see external heater coil inlet and outlet lines. In the photo on the lower right, you'll see those external heater coils. The jacket's removed from that car. They're welded onto the shell of the tank, and they allow steam to be circulated through the coils to heat the product if necessary for unloading. Again, commodities like asphalt, as they cool in transportation, are going to require reheating when they get to their destination to move out of the car. On the upper right-hand side, you're going to find some internal coils. These are more and more rare these days, but they do still exist out there. The inlet and outlet lines would have caps on those underneath the cars. We need to be careful in determining whether or not we're dealing with internal or external coils. The external will not have caps, internal will. Occasionally we'll get calls that those are leaking, and most of the time what we find is what's coming from those is water, which would be from condensation from the steaming process. But again, with internal coils, you've got to be careful because there's a possibility that one of those lines could have been damaged or corroded and actually has now product inside of it. So again, most of the time we're seeing water coming out of those, but you could have a situation where there's product in there. All those systems are periodically tested to make sure that they're intact for service. We see some cars that have multiple compartments. While it's not as common, they do exist. On the left-hand photo, you see a 3-compartment car. The right has 4. Each compartment will have its own manway and valves. While commodities may be different in each compartment, they're typically very similar. They could be different grades of a solvent or different grades of a commodity. They may be totally different commodities, but typically they're going to be compatible with one another in that car. The capacities for these individual compartments are going to be listed on the sides of the car at the compartment itself. There may be multiple placards on the car. The compartment numbers will be numbered from the B end of the car. As an example, from starting on the B end, you would have compartment number 1. Going towards the A end would be 2, 3, and possibly 4, which would be fully down at the A end of the car. Here's a DOT 105, I'm sorry, a DOT 111 A100 W5 tank car, which is transporting hydrochloric acid. It's a W5 car spec because, again, it's a fusion welded car that's made from steel, but it's got a rubber liner on the inside of it to protect it from the hydrochloric acid. You can see the fittings are also all rubber coated to help protect them from acid corrosion. This particular car is a non-reclosing vent style rupture disc. Newer models are including an external reclosing pressure relief device. Here's your external vent. Now for a third type of rail tank car, is cryogenic tank cars. You can see in the picture These are also uniquely identified by their physical characteristics. This Argon car does not have any fittings or appliances on top. All valves and PRDs are in the valve box on the side of the car. These operate at a lower pressure, but are designed to contain very cold materials. The DOT-113 is the most common cryogenic tank car. It is built as a tank within a tank, think a thermos bottle. The space between the tank has very efficient insulation, is under very strong vacuum to help with the insulation and to keep the material cold. Both the inner and outer tanks here are approximately ½ an inch thick. You'll see the specification that is a low pressure car, meaning that it's got less than 100 psi test pressure. It has a rupture disc which will fail at 90 psi and a reclosing safety valve that opens at 60 psi. Cryogenics need to vent to relieve built-up pressure as they heat up while they're in transportation. Generally, you can expect that the pressure will rise by approximately 3 psi per day on these cars. Regulating valves on these cars are designed to relieve that pressure in a controlled manner. The regulating valves on a DOT-113 are generally set at approximately 25.3 psi. You'll also find vacuum plates on these 113 cars. The plates are held on only by the internal vacuum between the two tanks. If a plate is missing or falls off after a derailment, it indicates the interstitial space has lost its vacuum and thus insulative properties. We'd expect this car to heat up much quicker than the standard 3 psi per day. Once it begins to heat, the regulating valves will do their best to control the pressure. If they can't keep up, the safety relief valve will open. If the safety relief valve fails to lower the pressure, then the rupture disc will blow, which will vent the car. Most materials transported in DOT-113s are inert atmospheric gases. BNSF does move some shipments of flammable liquid ethylene in the 113s as well. Liquid ethylene will not have regulating valves and is closely controlled by the railroad to deliver within a certain number of days to prevent overpressure. Cars equipped with regulating valves will say so on their side. You'll see in this picture an Argon car with the regulating valve venting normal sign there. You'll also find similar wording and stenciling on the sides of CO2 and nitrous oxide cars. It's not uncommon for railroad personnel or the public to call 911 when they see a placarded car venting in the yard. Here you see a CO2 car, carbon dioxide, liquid carbon dioxide car. It's in a DOT-105 pressure car. That car's got 5 inches of urethane foam insulation underneath the jacket that you see on the outside. This car's venting normally. You can visibly see the venting and notice that it does not extend down to the ground level. This would be loud enough to hear from probably about 5 to 10 car lengths away. The venting is through the regulating valves and again is completely normal. Here's another example of normal venting from a regulating valve on an Argon car. This is what we've considered to be not normal venting. You can see significant ice buildup on the valve box and a significant vapor cloud on the ground. Understand the hazards of the material. For argon, it's an inert atmospheric gas. It'd be very cold and displacing oxygen in the environment where the visible vapor cloud could be seen. If this were liquid ethylene, you'd have those same hazards along with the potential for a flammable atmosphere. Remember, always understand what it is that you're dealing with. Another example of not normal venting from the valve compartment. Not a great picture, but these valves and piping systems on cryogenic cars are complicated. Unless it's really obvious to fix by turning a simple valve that's labeled, we need to make sure that we're not turning things that we don't understand what they go to. Generally, in most cases, railroads are going to bring in the cryogenic company techs to fix and repair these problems. These cars have both outage and pressure gauges built in the upper left-hand side there. They may not be accurate when you first open the door. Typically, the valves behind them are going to be closed while they're in transportation. Don't open the valves or the cars, again, unless you're trained and you know what you're doing. Finally, for cryogenic cars, this is an example of the CO2 housing. This cryogenic again moves in that DOT 105 pressure car due to high pressures of the liquid CO2. Generally, carbon dioxide is loaded at about 200 to 225 psi. Here you'll see familiar devices such as the regulating valves, safety relief valves, and a rupture disc assembly. On the car, you'll also see one liquid valve and one vapor valve for loading and unloading the car. Which valve should operate normally in transportation? Remember, only the regulating valve is designed to vent the car under normal conditions. Safety relief valve or rupture disc device operation would indicate to us that there's a problem that must be addressed with the car. Once the CO2 car gets below 60 psi, the CO2 would convert to dry ice and just slowly vent off. All right, now we're going to cover a few other types of cars that you might see on the railroad or involved in an accident. Not all of these are going to carry hazmat, but some might. Auto wrecks. These are going to be similar hazards to what you'd have with a typical automobile, just multiplied by the number of cars that are in there, between 12 and 18 cars, and in some cases the accordion-style car there may have up to 32 vehicles inside of it. They're going to be double-deckers, meaning cars are on the top and the bottom. We've seen an increase recently in electric automobiles that are being moved, such as Teslas, and you got to understand if there's a fire or a wreck involving these cars, what it is that we're dealing with before we get too carried away with intervention. For electric car batteries, as you probably all well know, they can maintain a charge for an extended period of time. So don't touch or approach any damaged battery packs or exposed cables on electric automobiles. Refrigerated boxcars, these have motors and refrigeration units on them. The units are fueled by diesel fuel and can be manually shut off if needed. Newer units are GPS and satellite controlled. Remember, they're on for a reason, to keep something cold. Think about what's inside that container and whether or not it's absolutely necessary for you to turn it off before it's done. In some cases, entire loads can get ruined based upon temperature drops monitored inside the container. Fuel tanks may have a capacity of up to 500 gallons. You got to watch the plug doors on these cars. If they're damaged as a result of a wreck or collision, the tracks that the plug doors ride on could be damaged, and as you were to try to open those, the doors could fall off. Here are some coiled steel cars. With the cover on, they can sometimes be confused with a tank car. The covers are designed to be completely removed to access the very heavy steel coils underneath. Be careful around these cars in a derailment. The coils could become unsecured and be pushing against the covers if they're overturned. We don't generally move a lot of hazmat box cars, but they could contain smaller containers of hazardous materials. Because of placarding rules, some of these may not be placarded containers depending on the volume and the type of hazmat contained. Always check your shipping papers before approaching these types of cars to confirm whether or not there's hazardous materials present. Again, beware of plug doors on these units if they're damaged. People have been killed by them falling off the tracks. Here are some intermodal loads. You can find TOFC, which is in the upper left, that's a trailer on flat car, or a COFC, the lower right, which is a container on flat car. Sometimes, depending upon the setup, the doors to the trailer containers may not be accessible or able to be opened based on the orientation of the containers. If they're leaking, they'll likely need to be unloaded for inspection. A lot of times this will require us to move that car to a siding or a yard track to be able to offload the equipment for inspection. Most of our intermodal shipments are moved using articulated well cars. This allows for us to double stack containers for transport. Access again to these container doors can be an issue, as well as extended heights of the containers. Because of placarding exemptions, again, with the type of hazardous materials contained, placards may not always be present on the outside of the container, and again, it's always a great idea to check your shipping documents to confirm whether or not there's hazardous materials present. These containers carry anything from Fruit Loops to big screens to industrial chemicals. Intermodal tanks are commonly moved by rail. Here you can see a tank on a flat and 2 tanks in a well car. If loaded in a well car, the valves will always be in towards the center and in the well. It is not permissible to double stack intermodal tanks on well cars. These tanks are constructed like highway tank trucks, much thinner steel than tank cars, but with similar safety features. The frame that you see on the outside is not for structural purposes for the tank. It's simply to move it out and onto a different mode of transport. BNSF does not allow the Spec 51 or pressure intermodal containers to be shipped on our network. For regulations, the proper shipping name of the hazardous material must be stenciled on this tank. Secondary internal valves can be activated if the primary is leaking by identifying the pull cord along one side of the tank and pulling the cord to isolate the valve. All right, well, we're pretty much finished up with the rail car knowledge portion. I hope that you all have learned something from this presentation. Again, this is a map of our BNSF HazNet team. All of us are available. We strongly encourage you guys to reach out to us if you have questions, if there's training needs within your department. It's what we do. We all really like reaching out and what you guys do for us, so we're here to help. Remember to visit our website for First Responder, which is at www.bnsfhaznet.com. All right, well, I just want to say thanks again for everybody's time tonight. We truly appreciate what you all do for our communities and for the BNSF Railway. Make sure to contact us if you need any assistance, again, with training or preparedness for rail emergencies in your community. Also, visit our website. Again, BNSFHaznet.com for more information. As a reminder, you're going to get an email with a survey. Complete that if you could, please. We want to make sure that we're making these webinars as helpful as possible to the participants in the future. So I hope you all have a great evening. Stay healthy and be safe. Thank you.
That's different from the last one I did. A lot. I figured it'd be a little more information than that, but